Let's take a look at some of the descriptive statistics we would use on a pretty regular basis whenever we're analyzing any kind of data set as we go through. And for this, let's go ahead and simulate the rolling of dice, which is more or less random. So if you've ever rolled dice or have access to dice, you'll know how to do this on your own. But I want to use the Excel tools to do this. So what I want to do is simulate a roll of 4 dice, basically, as we go through. So let's generate some data for that. Rather than actually doing it ourselves, because I want to have a lot of observations, let's use the Data Analysis Tool Pack under your Data menu. And the tool we'll use for that is the random number generator. So let's create a variable for that. Let's create maybe 1,000 instances of that as we go through. And a dice roll is a uniform distribution, so we won't discuss all the possible distributions right now. But I know when I roll a dice, I'm going to get a number sometime between 1 and 6, and therefore when I roll 4 dice, I'm going to get a number between 4 and 24. So I want to generate random numbers from 4 to 24. And for reasons I'll explain in a minute, I'm going to tack a 0.999 onto that value as we go. And I want to take the output of this random number generation and save it in this spreadsheet. Let's just go ahead and put it over here in column C as we go through. So I'm going to create 1,000 uniform data elements from 4 to 24, starting in cell C1. So here they come. Okay. So there's my 1,000 elements as I go through. Okay, so now let's run some descriptive statistics on that to see what tends to happen as I go through. So I'm going to back up here to descriptive statistics to look at those 1,000 data elements. I want to look at the data elements in column C. There's no label in that, and I want the output range to be over here in maybe E1. And I want to take the summary statistics as I go. So let's run that summary statistics. So you saw this in discussion 3 in Unit 1. Okay, so there's our descriptive statistics coming back. It ran slow because I took all of column B for as low as it could have gone. Had I picked the cells from row 1 to 1,000, it would have run faster, but I'm just saving time as I go through here. So if I roll the 4 dice, the average value I'm going to get, according to this, in 1,000 observations is 14.13. The median value is 13.9. So that's not really what I want, because the random number generator creates, if you will, decimal values as I go through. So let's get rid of those descriptive statistics, or I'll keep them. I'll do it over here. What I really want is the integer value of that to represent the overall values that I'm looking for. I'm going to copy this down quickly to roughly row 1,000, 1,001. Going to take a second, because I want to know the typical roll of the dice as they come through, not the arithmetic mean of a bunch of random numbers generated. Remember, the random numbers simply simulate or generate our dice. They're not the dice in and of themselves. So I'm almost there. Okay, a little more. There we go. So down to there. Okay, so there's my integer value. So those are my real dice roll. I didn't really roll a 9.41. In that case, I rolled a 9. And that's why I tacked that 0.999 onto the 24. I wanted to be able to show the full range of all the numbers that would round out to just achieving the 24. So now I'm ready to take the descriptive statistics of that again. This time I'll show you how I pick the cells rather than the individual lines. I can just pick a range of values there as I go through. And that gets me there. So I'm going to save this output in column J so I can compare the two, and I still want the summary statistics. So if I run that now, I have a non-numeric input range. Where is it? Oh, because I didn't do that. I want row H here. I must have accidentally hit something up here in this value as I went through, so I'm going to shift back to column H, and there's my values as I go through. Okay. So now my mean is 13.651. So that could be a decimal because it is in fact a mean, but my median now is a 13. So my median value, half the 4 dice rolls gave me a 13 or less, half gave me a 13 or above. The mode was a 22, so I got a lot of 22s for some reason. I had a variance of 37.7. Square root of that is a standard deviation of 6. That's what you're seeing in your descriptive statistics. I've got a very slight negative skew toward the left. Kurtosis is a flatter the curve than I would expect, and a skewness that's pretty close to 0. So it's a pretty balanced curve, a little flatter than usual, which doesn't surprise me because the outlying values are just as likely on a die. A 1 and a 6 are just as likely as a 3 or a 4 on an individual die as I go through. So there's my descriptive statistics. So the question is, could I use this to do inferential statistics? And the answer is no. I haven't really modeled a 4 dice system, have I? When I roll 4 dice, I'm very unlikely to get a 4, because that would require me to get 4 1s, and I'm very unlikely to get a 24, because that would require me to get 4 6s. I'm much more likely to get a 14, where there's lots of different combinations of values that would kick in. It isn't really a uniform distribution. So although I can run the data and I can run the statistics, the fact that I have descriptive statistics doesn't really mean I've represented my data. You as an engineer have still got to evaluate and plan for all that data accordingly. So let's get rid of, I'm going to get rid of some of these columns here just to make things a little neater as I go. And instead, let's take a look at how I would really model 4 dice as I go through. So let's go back to data analysis and generate our random numbers again, only this time let's do it for something that would look a lot more like the experiment we're actually trying to track. So I really want to roll 4 dice, not 1. So let's make this a 4 and still run a 1,000 distribution. And for each of those dice, I could get a number from 1 to 6. Collectively, they'll add up to 4 to 24, but each individual die could get a number from 1 to 6. So I'm going to tack that 0.999 on, just like I did before, as I go. And then I want an output value that I will put here in column M as I go through. So let's generate that kind of data as we go through. So now there's the data I really want. So I want the integer value of those, right? So I actually see the dice roll that represents. I've got 4 of them. And then I want to take the sum of the 4 rolls. Okay, so that first roll is an 18. When I rolled a 6, a 5, a 6, and a 1 on my dice, it added up to an 18. So I'm going to take those rolls, and that's what I want to do 1,000 observations on, which again will take a second to scroll down. Those of you who know Excel could probably do this faster than me. If there's some trick you have, feel free to share it with me, but I only know how to do it this way. Halfway there. $800, $900. Okay, so now I'm just about, okay, there I am. So there's my 1,000 observations as I go through. What did I do wrong here? I did something wrong on my equation here, so I must have, let's do this again, 2, oh I see, I did the, should have clicked here. Alright, so I did that wrong. So, we'll fix that right now. One, there we go. My apologies. So you got to be careful with Excel as you go through. Okay, column U now has a dice roll in it that we want, so we can hide all this other some of this other nonsense that we have. Okay, so there's our 4 dice roll for real now. So let's do a data analysis of that with our descriptive statistics. Okay, so we're going to do column U this time. Okay, we're going to put our results here in W. And we're going to do summary statistics. Let's let it roll. So there's our summary statistics of the real data as we go through. Okay. Now in this case, our mean now is 14.081. Our median is a 14. Our mode is a 14, much closer to what we'd expect. That is near the center. So we're not being thrown off by that. Our variance is now down to just under 12, so standard deviation of 3.4. And the range of values is a range of 20 from 4 to 24. So in each case, we got, if you will, a range of 20. Okay, so we're seeing the same basic range of data. So numbers were generated over the entire sense of the data. But notice the standard deviation difference. When we only had one number, we ended up with data that was really, really wide, with a standard deviation of 6. 6 is a pretty large standard deviation, considering the data values only go from 4 to 24. The fact that most of the data falls within 18 of that, or 3 standard deviations, doesn't really help us very much. It's not really a curve. At 3.4, we see that most of the data falls within 3 standard deviations of that, or roughly plus or minus 11. So we're much more likely to get anything from a 3 to a 21, then we already get outliers beyond that. And that's more what we expect to see in our data as we go through. So the difference is that in the first range of data, I simply modeled random numbers from 4 to 24. As though all were equally likely. And when you roll 4 dice, that's not really the case. You really have 3 degrees of freedom, because on one dice you might get a 6 at the same time another one gives you a 1 or a 2. So the fact that some of the die go high and some of the die go low means they'll tend to cancel each other out with the freedom that they have on the roll, so that the number you end up with tends to be closer to the center than it would be in the uniform distribution. And we see that here in the smaller standard deviation. There's less variation in the data because the differences in the freedom of each individual die to be high or low tend to cancel each other out. And we didn't have that on the earlier case. The visual cue you want to go with is to remember that in empirical statistics, most data falls within 3 standard deviations of the mean. So when the range of data is only 20 wide and 3 times your standard deviation is almost that much, something's probably wrong. So the second version of the descriptive statistics is much more likely to be true and would very accurately be used to predict what the next 4 die roll would be. The first set of data we had would not accurately predict anything going into the future. It would tell us nothing about what the next 10 or the next 20 or the next 30 4 die rolls would be. But we get a very accurate prediction out of the one on the right. So if you build your statistical model to take into account the degrees of freedom of the process you're actually modeling, you'll end up with descriptive statistics that are both accurate and useful for making inferences and predictions about the future.